All right, so section 30 is on ensemble methods, and it used to be like 3 different sections. So just to explain what the parts are. So first we have random forests, which is going to be the first section on like an introduction to ensemble methods, and which basically consists of boosting and, just bagging. And then we have grid search, which is something that I'll actually talk about in the next study group. And then we have boosting. And so there's kind of like 2 main concepts that we'll be talking about today. Hopefully we'll get to both, but bagging and boosting. And these are all ensemble methods that we'll be talking about today. And as I was mentioning before, I forgot if I said this before after I press record, but because there's a lot of material to go through, it used to be like this material used to be covered in 3 separate study groups. So if we don't make it through to, if we don't make it all the way through, I'll actually push support vector machines till one of the office hours for our mod 3 project, or have like an additional day during project week, just because that is just an algorithm on its own, but these you can use in different ways, and I think is more important to focus on for now. Hi, Kishore.
Yeah. So we already have one section of, I think, 21, which is the office hours. So
that's
this
right.
Also, okay.
Yeah, I think like as support vector machines will not take more than half an hour. Okay. So it should be like one of the shorter ones. And then object-oriented programming also going to be a fairly short one.
Oh, okay.
Awesome. So any other questions before I get started? All right, so this study group, I actually have it in 2 parts, one of which is talking about random forest, and random forest actually is kind of sort of within bagging, but not exactly, and I'll explain why later. And then after this whole section, random forest, I actually took 2 slideshows and put them together. The other section will be on boosting, and that's like things like add boost, gradient boosting, XG boost, words that you might have heard before. But all right, let's get started with forests. So to get into forests are actually built with trees, and we talked about decision trees last week. And if anyone has anything to clarify about decision trees, just let me know. But we're going to do a quick review of what they are. We're going to talk about bootstrapping and aggregating, which is shortened to bagging, and that's what bagging stands for, bootstrapping and aggregating, 2 decision trees. So the way that that is phrased basically implies that bagging can be done for any other algorithm, which is pretty cool. But I'll be talking about bagging in the context of decision trees. And then random forests is an algorithm that is completely different from bagging. Not completely, it's just some intricacies that are slightly different, but we will go through how they work. I think that tree models are extremely important to know. 1, because they are very popular, and 2, it's actually, at least in my experience, the one that is asked about most in interviews. So I think it's important to know how they work. Most specifically, the random forest algorithm. So just so you all are aware. All right, so quick review of decision trees. So decision trees can be used for both regression and classification. Their cost functions are different, but kind of similar. The cost function for regression trees basically is, I think, like the average away from the dividing line. And then for classification trees is you either use a Gini coefficient or the, what's the other one called? Something about, there's one impurity and there's one called, I can't remember off the top of my head. Oh, entropy is the other one. So you're looking at how pure are the splits. So I don't know if y'all talked about this last week, but trees do have a bunch of pros and cons. Let me just skip through these diagrams really quickly. The idea of a decision tree is you are just segmenting your data set based on the differences in your input data. So sometimes you would visualize it like that, but the conditions on which you split are mostly visualized like this. And I believe in the code, and I think in James's notebook that he shared, he has code for outputting this, if I'm not wrong. All right, let's get through this pretty quickly. One huge problem with decision trees is you're actually very prone to overfitting. So if you imagine if you set your one of the hyperparameters that you can set for trees is the tree depth, and that just means how many layers you split. So in this case, I think this is like a depth of, I'm just going to estimate like 10. That means you can go 10 levels deep. And the depth of the tree is something that you can actually tune as one of the hyperparameters. When you have a deeper tree, and I think you would set that, I think it's max depth. I think that's the literal name of the hyperparameter. The deeper your tree is, the more prone to overfitting you get, because in your training data, your, I guess your classification tree is going to end up with a lot of different possibilities, or a lot of different end nodes. And so that leads to overfitting, because, you know, if you have something that, if you have unseen data that just follows a path, and, you know, it follows a more and more specific path each time, and because the order of the conditions that you're testing for don't change, it does lead to overfitting. And that's a huge problem, which is why actually decision trees aren't used by themselves very often. Questions so far? All right. So trees are great. This is not my slide deck, by the way, but trees are great. Okay, so an overview of decision trees. Advantages, they work well with nonlinear relationships, as you saw with like a tree regressor. If you use a tree regressor over a linear regression, you don't have to worry about all these linearity assumptions, right? So it works well with nonlinear relationships. They're easy to interpret. You just have all the conditions at which you're splitting. It does implicit feature selection. So you can actually throw in as many features as you want, and it would do that for you, because in tuning and deciding what the best split is, it is implicitly selecting features for you. I'm not sure if this was shown to you all, but you can actually extract what the most important features are in your trees. And it also accounts for interactions as well. But on the other hand, there are a lot of disadvantages, the main one being that they are overfit, especially if they're completely pure. So completely pure, you can sort of imagine, let's say you have your decision tree all trained, and you have like a really large max depth, maybe a depth of like 20 even, such that the end of every node is pure. That means that, like, let's say you're doing a binary classification problem, all of the training samples that end up at each end node, it's going to be uniform at each end node, if that makes sense. So the first end node will be all class A, second might be all class B, and that does lead to overfitting, because only if you have like a data point that follows a certain path, that one, it just is based on, I guess, the data that was trained on. Instability as well. Small changes in the input data can cause large changes to the structure of the tree. Imagine if you're taking different subsets of your training data. Let's say you're doing cross-validation. If you were to do cross-validation on decision trees, you actually do end up seeing very, very different results. And then this book, Elements of Statistical Learning, which I think I sent you all the PDF of a couple of weeks back. I would say this is the best book if you want to like really get into the weeds of any machine learning algorithm. Definitely read that book. But a quote from there is apparently that trees are really inaccurate. Questions so far? All right, so the idea of ensemble methods is based off of this wisdom of the crowd idea. So wisdom of the crowd basically comes from this like 1900s statisticians experiment, where I'm sure you've had those games where you like, I don't know, guess how many jelly beans there are in a jar. In this case, they were guessing how heavy this ox was. And what they found out is if you had like a, I guess, professional guess how heavy this ox was, the probability that you get the correct answer is going to be further away than if you actually take some aggregation of a bunch of random people's guesses. So let's say I wanted to guess like the height of the Empire State Building, and you have like, I don't know, a professional like height guesser versus like you're surveying 100 people. What this is saying is, and it's actually sort of been experimentally proven, that the average of the 100 guesses will be more accurate than the professional's opinion. And that's just where the idea of doing ensemble methods comes from. Questions about this?
Well, one quick question. So this will be like more based on a lot of different methods giving you the results and like you take the average of those results?
Yeah, exactly. So I think you actually in your project, you use something called a voting classifier. And I'm
Yes.
actually going to talk about voting classifier in a little bit. But a voting classifier, or actually in your case, you use the voting regressor. What a
Correct.
voting regressor does is, let's say you have your linear regression, you have like a ridge, a lasso, and maybe a forest regressor. It's
Hmm.
actually going to take in all four of them
Hmm.
and return you, I think, either a weighted average or, yeah, probably a weighted average based on its overall accuracy.
Okay.
And yeah, and in like a voting classifier, basically, if you have 10 different classifiers, a voting classifier, how that works is it will run your test data through all 10 classifiers. And let's say like six of them vote that it's class A, four of them vote it's class B. The output will be that it's class A. So
Okay.
that's how the voting classifier works. And I think I actually have that in a tab up here. If I can show it really quick. Yeah, here we go. Voting classifier might be something that y'all try using in your projects. But here you can see that one of the parameters that you put in is actually a list of parameters. Sorry, a list of estimators. So what you would do here is you would first instantiate all your models and then literally feed them in as a list, and it will run your data through all of these classifiers, which is, I would say, I think one of the simpler ways to use an ensemble method. Cool, since I've talked about this, it close this out. All right, so, oh my gosh, I just closed my slides. Sorry, you guys. Oops. Okay, this works. Okay, so the takeaway is that we can learn a lot by combining many different learners. And so the whole idea behind this is that, you know, you have this group of weaker learners in like my earlier example about guessing the height of the Empire State Building, people who don't really know much about guessing heights, but 100 people who are not so good at guessing heights, which we're going to call the weak learners, can get you a more accurate result than your professional, your single strong learner. And so anything that combines multiple models is an ensemble method. And so random forest is also an ensemble method. Later, when we talk about boosting, those are also ensemble methods. So ensemble methods is the umbrella term for all of these. So here, just to summarize, in essence, we can combine the output of models that are not accurate enough on their own to get the wisdom from the crowd. Cool? All right, so first we're going to talk about bagged trees. So bagged trees is one form of a bagging algorithm, which is a form of an ensemble method. So these are the steps for a bagged tree. First, we're going to do, and again, bagged stands for bootstrapping and aggregating. So here you can see we're first going to bootstrap the entire data set, and we're going to talk about what bootstrapping is in a little bit. We're going to build a tree using the bootstrap data set, and then we're going to repeat step 1 and 2 many times and aggregate them all. And then we're going to output these predictions, and we'll look at these as we move through these steps. So first of all, what is bootstrapping? So because trees are very prone to overfitting, we're actually going to take bootstrap samples with replacement of our training data to create different mixes of samples, if that makes sense. So here we have our original sample. Our bootstrap samples are going to be of the same size as our original sample, but these are all sampled with replacement. So each data point has an equally likely chance of being selected again at every step of selecting a new sample, if that makes sense. So these bootstrap samples are created by just drawing with replacement from the original sample. And the good thing about that is you end up with slightly different mixes of your data set with every bootstrap sample. So that's the whole idea of bootstrapping.
What are the chances that like the data point is repeated?
Oh, actually, depends on the size of your data set, but the idea is it doesn't matter if your data point is repeated. The idea is we actually want that, or we don't want your data point to be repeated per se, but you just want to get a different mix of data. Like for example, maybe your, perhaps your, how do I explain this? basically you're just getting a different subset, but from the same data. If that makes sense.
Okay.
Yeah. So it actually doesn't. What it would be kind of preferred to like sometimes have repeated points, sometimes not. You just want to get some variation in your training data so that your trees that are trained will turn up different, but still kind of representative of your data set. So after the bootstrapping, and this is just an example, here you can see we have 4 rows here, and each row is an observation. And in the Bootstrap dataset, you're just picking with replacement. So randomly, this is a Bootstrap dataset that picked out 2, 1, and then 4 twice. And there's nothing wrong with this being repeated. And then what will happen is a decision tree will be trained on this multiple times. Well, different Bootstrap datasets just over and over again.
Hey, Ish. I might have missed this, but when you're bootstrapping, do you want your total number of data points to be the same as the original data set?
Yes. So okay. You want your you want your Bootstrap samples to be the same size as your training data.
Okay, yeah, I did miss that. Okay, cool.
In Bootstrap sample 3, that's kind of unlikely. You know, go back to the previous slide, because there are 3 blue dots in the original, but then you end up with 5, but this still can happen basically.
Yeah, because you're sampling with replacement. So what's technically happening when you're drawing these 9 is you're drawing 0.1, you're putting 0.1 back, you're drawing the second one, putting it back, third one, putting it back. So that's how you get that variation. So example of Bootstrap dataset. So next is the aggregation step. So once you have all of these Bootstrap samples, you have a decision tree for each sample. And each tree will have a low bias and high variance, meaning that it's quite overfit to the bootstrapped sample. And so you're going to repeat this process again, and you have a bunch of kind of overfit trees. And something that you can actually tune in this bagging classifier is you can actually tune, different aspects of the tree. Typically, you're training the same kind of tree on your different bootstrap samples. If that makes sense. So you would instantiate your tree first, instantiate your decision tree first, and then train that tree on different Bootstrap samples. If that makes sense.
So how is this different from adding features and then running regressions?
Yeah, so pretty different. So this is basically, you're not changing the features, you're only changing like the rows, if that makes sense. So maybe, so like on your first tree, you're training it on rows like 1, 2, 3, 4, 5. Second tree, maybe you're doing like 2, 2, 4, 5, 3. Third tree, you're training on basically a different set of rows from the same training data set.
So it's like, let's say there are like in my training data sets, out of 100, I've picked 80. And within that 80, what I'll do is I'll select 20 for running first time, and then another 20, or the entire data will be used.
Yeah, so not 20 at a time, but you're going to use the whole 80, and you're just going to, I guess, take random, you're going to shuffle that 80 each time in this method. So here, instead of 80, we have 9, but we're going to create these Bootstrap samples that have the same size as this, but they're just still being randomly drawn. So in your case, you're going to take the 80 points, we're going to do the same thing and create like strings of 80 that are all different, and just running a single decision tree on each one.
Is it selected automatically, or we need to specify some functions?
It is selected automatically, yeah.
Okay. We just mentioned it as like, okay, pick any random thing and then run it.
Yeah, I'm pretty sure it is. I'm pretty sure it's built in. But we can actually check if, let's see if I can, if I have the
and also
here.
Yes, question is this process how is it computationally? Like, is it more intensive? Is it, or can you explain that?
Great question. It's actually computationally very, very extensive, because you imagine training a tree. I don't know if you all have already ran decision trees, but training a tree takes pretty long, especially if you have a big data set, especially if you have a lot of features, because every feature is another dimension that it has to look for the best split. So it is very computationally expensive because of that. Yeah. And then, yeah, here, back to bagging classifier, you see here, Bootstrap is equal to true by just automatically, by default. So,
and then
any other questions?
Yeah, so with it being intensive, could you maybe like talk about, well, in a particular situation, okay, even though it's intensive, it makes sense to do this in that situation?
Yeah, so random forest or bagging. Actually, I will say that bagging, especially bagged trees specifically, not used as much as random forest. We'll actually talk about random forest right after this, and we'll actually talk about why random forests are preferred, and also random forests are just really, really good for not overfitting. Cool. Something else I wanted to point out as like a mild tangent is in this bagging classifier, if you end up trying a bag classifier for your project, here you can see base estimator equals to none. So nowhere in this says that you're treating a decision tree, which is interesting because bagging classifiers, you can actually use any classifier. I'm just talking about it in the context of decision trees. So here you can see base estimator, default is none. So you can actually choose a specific algorithm to bag, but by default, base estimator is a decision tree. That's just something that's good to know. But you can really feed it in any other already trained classifier. Not already trained, any other instantiated classifier. Cool. All right, so back to this. And I want the presenter view. There we go. So yeah, so
sorry to keep interrupting you, but I have a question about this slide.
Worries.
What does low bias and high variance mean?
So low bias and high variance means basically high. I just think of that as overfitting. There is a diagram that is in one of the notebooks. I think it's in the logistic regression notebook. Actually, let me pull it up real quick. I have it here. Let me launch my Jupyter real quick. That's just a good diagram to remember. Let me just make sure I have it in the right place to show you all. Here we go. So this is the bias variance, one of many bias variance diagrams, but I like this one a lot because for decision trees, which are, decision trees have low bias and high variance. Basically, and this is here, you can first think high variance because the decision trees, and this is actually when you're looking at what is being predicted. What is being predicted, if you have a decision tree, because it's so overfit, the error of your data points is going to be quite sporadic, if that makes sense. And then in the low bias sense, is talking about, I guess, the precision of your data. I personally don't really think about models in that specific way, but I usually look at it just in terms of either high or low bias or variance. What I'm trying to say is I usually like associate either one of these with like overfitting or underfitting. Does that make sense? So if I ever see low bias and high variance, or just low bias or just high variance, I think overfitting. But if I see high bias or and or low variance, I think underfitting. And I think that just makes more sense to me. I don't know if that was helpful or not.
Yeah, yes, it was.
Okay, great.
Going back to that, can we go back to that the target diagram?
Yeah, absolutely.
So we want it to be, one sec, sorry, I'm getting a call. We want it to be high variance and low bias, but it looks like don't we want a model that's more accurate? And it looks like that's like the least accurate, even though we're doing like, we're generating a bunch of them.
Yeah.
Like, how does that benefit at the end?
So at the end, you usually, what's accurate, I guess, with this diagram, you would assume, yes, you want both low bias and low variance, right? But for most models, because of the variability of data that just exists in the world, you are looking at some trade-off between this and this, because this would be like results of like an overfit model, or I guess this would be as well, but overfit in different ways. This would be systematic overfitting, and this would just be, I guess, just, yeah, an overfit model that just has like random errors. I don't know if that makes sense, but you usually want to find some trade-off between this.
Mm-hmm.
Yeah. I don't know if that answered your question.
Yeah, I think so. But because like random forest, we're doing that. Wait, that's what we're talking about, right? Just making sure random forest. No, okay.
We're talking about bagged trees currently.
Okay, bagging trees. But that's like generating a whole bunch of them, right? A whole bunch of them models.
Yes. Yes.
Okay.
Yeah. So you're generating a whole bunch of them, and then basically, like, let's say you have 100 different bagged trees, trees in your bag, I guess. It'll be sort of like a voting classifier like this, and whichever class is predicted most will be the class that is your final prediction, and then regression will be an average.
Okay.
Yeah, so the way it works is, even when you're predicting, you're actually going to feed your test data through all like 100 trees in your bagged data set, and then it'll sort of like vote on what to classify your point as.
Okay.
Anything else? Cool. At this rate, I think we're going to have to split this into two, but no worries, no worries. We will cover everything. Okay, so yeah, voting method, as you see here, you have different, this is not random forest exactly, but different bag trees that are being trained, and then you have your majority voting and you get your final class. All right, so bootstrapping plus aggregating is bagging. There we go. So as you can see in a decision tree, you end up having that, if it's a single decision tree, you end up having this kind of overfitting. I'm guessing this is a decision tree with a pretty high max depth set. So because of that, it actually is trying to like get it as pure as possible, such that imagine like, you know, a point, an unseen data point that ends up being somewhere like here. An unseen data point that's there just based on this diagram. It could be blue, could be yellow, but this would classify it to be yellow, you know? But with, you know, this, with bagging, but by just using multiple trees and aggregating it, you end up with a more smoother decision boundary. And so it does, I mean, these technically I would assume are kind of like outliers anyways. So you have a smoother boundary between your classes. It's not trying to account for all of these tiny things, which is like overfitting. Gotcha. All right. So next up, we're going to talk about something. This is a concept that's actually used in random forest as well, but out-of-bag error. So out-of-bag error is a more efficient way of doing cross-validation. So generally, out of your training set, 2/3 of the observations will be trained on each model. I've also linked an article of why 2/3. It is not always 2/3. Depending on your scenario, you might change it, but very unlikely you will. Typically, it's 2/3. And yeah, as I think as Marv was saying, training trees extremely computationally expensive. Once you have a new dimension, it adds a whole nother layer of like searching for the best split for each tree. So imagine like training a bunch of trees is going to be very computationally expensive, and plus doing cross validation, like per each tree, training it 5 separate times, even more expensive. So therefore, you within your train test split are sort of like doing another train test split, where you're taking out of your train data 2/3 to train and then 1/3 to test, rather than doing the cross validation over and over again. So what we're doing here, just training your tree on 2/3 with the 1/3. You're going to look at every observation and make a prediction for each of the data points for which the data points was not used to create the tree. So that's just known as an out-of-bag error, just because in bagging, if you were to do cross-validation for each model, very, very computationally expensive. Questions about this? Cool. So yeah, it's just a form of cross-validation you're sort of like doing the cross-validation at a different stage compared to regular cross-validation. So typically if you're doing something like bagging, you don't have to do cross-validation. So issues with bagging, trees actually end up being correlated to each other. There might be a feature that is very powerful in generating separation between different categories, which results in trees being very correlated. By correlated trees, it sort of means that, like, for example, you have in determining like, let me see, what can we determine? In determining like, maybe you're classifying whether something is poisonous or not, maybe the color is a very, very obvious, it's a very, very important feature for determining whether something is poisonous or not. And because of that, it's very likely that you have very similar splits at the top. And the way that trees work is if you have like the same things at the top, sort of leads to more correlation as you go on. So despite being for bootstrap samples, you might end up with a lot of very similar trees either way, just because, you know, you're still training it on all of the same features. And so one thing to emphasize here is we're using the same features at every time you want to split the tree. And that does sometimes lead to correlated trees. Questions about that as we lead into random forests. So
one thing. Now let's say like we have the data. Now the heart data, right? In that data there is like sampling which says that when clotting happens in the heart, right, there are certain colors which are specified. So they say that there is difference in different colors of the blood when the clotting happens, at what the clotting is. So in that, like if we like create a feature, right, stating that, okay, if it is this color, say 1, and for everything else you say 0. So you have created one feature, and if you run the same feature here, right, while you're doing the bagging part of it, will the result change?
Oh, that's interesting. So turning something from, okay, so I think I understand what you're saying. So if you notice that like you have, let's say your very first split always ends up being the same split, you can just turn that into a feature. That's actually really interesting. It's not something that I've seen before. I imagine that because it turns something from like a feature to literally like a row, could be, or you might end up with the same problem of like, it will just go to that new feature and then just say, okay, all the zeros are going to be left, all the ones are going to be right. So I'm actually not too sure I have to like think about it mathematically more, but that's an interesting take, honestly. I'm not too sure what the implications of that are. Okay. But random forests will help mitigate that problem to begin with.
Okay.
Cool. All right. So, all right, random forests. So random forests, kind of similar. What we're going to do is we're going to bootstrap the entire data set. And the main difference here is instead of, you know, creating training these decision trees on the same feature set, you're going to be using a random subset of features at each node from the bootstrap data set. So that just kind of forces your trees to be evaluated differently, because maybe at the first split, you have this very, very important feature of like, you know, color of the blood in like determining blood clots. In some trees, there's a chance that that feature wouldn't even be considered. And there's even more randomness introduced in this case, because the subset of features considered at every step of the tree is going to be different. You're just going to randomly select the number of features at every split. Questions about that? All right, and then the rest of the steps are the same. Once you have all of these different trees built with different features, same thing, you're just going to aggregate the trees. I think this is literally the same as the last one, but yeah, you are taking the average of the prediction for regression and then taking the majority predicted value for classification.
If you bootstrap the entire data set from the outset, or you just have a different data set, then what's the point? Because you're working with a totally different data set.
Yeah, good question. So bootstrapping the data set, you're switching up your data set on a row level. So you're just taking different observations. This second part of feature subsetting gives you subsets of columns. So I think inevitably, I think the idea of this is that in bootstrapping, sometimes you might end up with like, very correlated patterns in your data set, or like between bootstrap data sets, you still might have very similar patterns, especially within some of the more important features or more significant features in this sense. So it's the main different thing about this is that taking the random subset of features means that maybe for one tree, you're not even considering the top 3 most important features. It is random, so it's not always the case, but it's possible that you're not considering the top 3 most important features, and then you're just building your tree on all of these other features, and your tree will end up looking quite different. Your trees do end up looking quite different. I know that.
And then you keep repeating that. You keep bootstrapping it again and again. I see in step number 3. So you really are using the whole data set in the end.
Yes. Yeah. You're right. Yeah, you're using the whole data set, just like I guess different parts of it at different trees, because you are taking random subsets on a row level and on a column level. So you're introducing randomness across 2 different dimensions.
Okay.
Or yeah. Mm-hmm. And so because of that, random forests they really protect against overfitting to a single feature, because just by like random picking, there's almost no way that you get you won't consider it like the most important feature for all the trees that you're training. Cool. Any questions about this so far? All right. So kind of similarly, we have this bootstrap data set here, and then with this bootstrap data set, so again, this is probably, I think, yeah, this was the same example from before, where this is like observation 2, number 1, number 4, number 4 again. With this bootstrap data set, for our very first tree that we're training, you can choose like a subset of 2 features, for example. I do believe that I want to say that I don't remember the default, but the number of features that you have in your random forest, I think, let me see if I do see it here. But I do think that I don't see it here right now, but I think it's actually a pretty low number of features that you choose at the very start. Let me see if I can see it real quick here. Oh, here, the number of features to consider when looking for the best split. So with each tree at each node, you're only going to consider a small number of features. So I believe that here, if auto, and that's the default, you're only going to select a square root of the number of features that you have. So the more features that you have, the smaller in relation that number will be. So let's say you have 100 features, you're only going to do 10 at each time. So you can imagine you're going to miss out on your important features quite a lot. So yeah, that's by default, you end up picking only square root of the number of features you have in your entire data set. Questions on this? But yeah, this is something that you can also tune and just see if it changes your model. All right, so really quickly, random forest just decorrelate each of the decision trees by ensuring that only M features are considered for a given split. So I think you can see here, I want to say that like square root is the smallest number of all of these, but you can see here, these are the out-of-bag error rates, which is, if you remember, each tree is trained on 2/3 of the bootstrap data set and tested on the 1/3. And so these are the error rates of the 1/3. And N estimators basically stands for how many trees you're training in your random forest. And so it sort of converges as you have more and more trees, but you can sort of see here that square root of the max features gives you the lowest error rate. Got it? All right. Any questions so far? All right. So let's see. Let's skip on this part. This is a quick showing of like the difference between random forest and bagging. So here you can see our out of bag error for bagging and random forest. We're going to look at the blue and the green lines. Typically, because random forests have even less overfitting, you end up with a lower error rate. So you can see here, the blue line, which is the random forest, has a lower error rate than bagging. I believe, yeah, this is number of trees as well. All right, so some really quick advantages and disadvantages of random forests. Very, very powerful, will always outperform decision trees just because it accounts for the overfitting that decision trees does. It detects nonlinear relationships well. This is the same advantage as a decision tree. And it is harder than other models to overfit. Disadvantages, they're not as interpretable as decision trees because with decision trees, you just need to be given the split and then you know how to interpret the tree. But with random forest, you're actually building like 100 trees or possibly more. And so you can't interpret it in terms of like, all right, if this data point is more or less than this split, it's likely to be what. And then also there are many hyperparameters to tune. And we're actually going to talk about grid search at the next study group. But yeah, grid search is your friend. So really quickly, just an overview of some of the hyperparameters. N estimators that I mentioned is the number of trees in your forest. The criterion, and this is for classification. So random forest classifier is the same criterion as decision trees. It's Gini or entropy. This is, again, something that you would just sometimes just test both and see which one works better. Maximum number of features. Again, this is the one where you're picking square root of the number of features that you have. The max depth. Again, because you're looking at such a small subset of features at each split, you can actually make your tree deeper just to see how it works. And then because of the different voting of the different trees, you might end up with very different results. But max depth will make each tree more overfit to the data set.
Yeah, one quick question. So is there any number that is for the maximum depth, like, okay, allowed, or it says that, okay, if it is like 3 levels down or 5 levels down,
yeah,
right, acceptable, or right, it does not have any limits to it?
So there's, I believe that there is like what is it called? Let me just quickly look. Random forest. Let me just look at this real quick. There's one that basically says you will not, if you don't set a max depth, or there's like something that you can set so that it'll keep splitting your tree until every observation is in a separate end node. So here, you see, if you have none, nodes are expanded until all the leaves are pure, or until all leaves contain less than the min sample split. So I guess this also goes back to min sample split, which is like the minimum number of samples. Let's say at a node, you've already split, but in this node you have 2, it won't split it anymore. So it kind of comes hand in hand, but let's say you have min sample split to be 1, or actually, yeah, 2 makes sense because you can split 2 more into 1. But if you don't have max depth set, it will keep splitting your tree. It will keep getting deeper and deeper until all of your end nodes are pure.
But
and leaves are pure.
My question is like, is there any suggestion that like, okay, you should have, let's say, 20 as your max, or?
No, there isn't. No, not to my knowledge. To my knowledge, there is no like guideline for what's a good number of like how deep to go. Usually, when you're doing an ensemble tree method, you don't want it to be very deep because it gets much more computationally expensive. So because of that, typically people don't go to more than like, I don't know, I feel like if you were to do like 100, that would be overkill. But most of the time I see like between like 10 and 50 because of how much time it will take. So I would say for your project, or if you want to use a random forest for anything, And I will explain this with, when we talk about grid search, you can actually, grid search is a way of basically testing different parameters all at once. But maybe you want to test like 10, 50, 100, and then just see which one is giving you the best result, and then maybe explore and like divide and conquer and search like that, if that makes sense.
I mean, till when the system would not crash. That's
Yeah. Yeah. Random forest is actually, I think, one of the first ones that will make your kernel die, just because it is computationally expensive.
one of my concerns, actually,
Hmm.
because the other day when we were doing decision tree itself, right?
Yeah.
What do you say? James could not run the entire thing.
Notebook.
Yeah, entire notebook, and could not run. And I did not see it as a very large thing. But then, if that's the case here, if the tree goes deeper and deeper, then I mean, I'm sure like the system would not take so easily.
Yeah. Yeah. Random forest, because you imagine you're like, when you're trying to find the best split, so storing like your RMSE values or your entropy or Gini values at every possible split. And so, and it is doing that through gradient descent as well. So storing all of that information, and it can be very like both memory intensive and computationally expensive. And also in your random forest, you know how you were able to like output the trees for your decision trees. Once you've trained a random forest classifier, you can actually also output, and it will actually give it to you as like a diff of like 100 trees and 100 different trees. Typically people don't look at that because you don't need to look at 100 trees for this. But yeah, harder to interpret, but yeah, very computationally expensive. And it is storing a lot of information, which is why if you do find your kernel dying, we can talk about like maybe like making your data set smaller, or just like cutting out certain things, like cutting out certain features from your feature set. But hopefully not all of you have to do that. Let's see, where was I? So yeah, next step is something Bootstrap. You can actually choose to bootstrap or not bootstrap your random forest. And also you can use your out-of-bag score. And I think out-of-bag score is something that you can actually output for each tree, which is pretty cool. And then njobs. Njobs is something that's more about the computer hardware. So how much of your, the way I understand it, I don't fully understand like computer hardware, but the way I understand it is like how much of your computer's, I guess, computing capacity you want to use to train your trees. Which,
the cores. So like you have, like the quad core has 4 cores.
mm-hmm.
So you can select the number of cores that you want to use it for this. So the other day I had this question for James as well, like which all, let's say the regressors or like the njobs can be used for, right? But then I could not get the answer. So even I have been searching for it, but then I see random forest we can use in jobs. So I think
yeah, and I think the using all is, I think -1 is what you would put.
Yeah, -1.
Oh, none means 1, sorry. And then -1 means using all processors. And I, from experience, know that if you use -1, your computer fans will go insane.
Yeah, if you're doing only that work, then like your -1 is the best one.
Yeah.
Like if you're working multitasking, then right, you would not be able to do anything then.
Yeah. Yeah. So I mean, I feel like probably for most of the data sets that you're doing for this project, you should be able to get away with just 1 and won't have to wait more than an hour. And that's actually not that bad. But I will talk about grid search at our next study group. It is actually included in this section as well. But in our next study group, I'll talk about grid search and how you can use that to make your modeling process a lot easier. But yeah, any other questions so far? All right. Let's see. Okay, really quickly talking about feature importances. With decision trees, you were able to get this information as well. Basically seeing like which feature contributed to classification of your data points more. So you can actually get this as well. The more the accuracy of the random the decrease in accuracy due to the exclusion of variables, the more important the variable is. So basically they're comparing a bunch of different trees. If the variable wasn't considered and it affects the accuracy of your tree a lot, that's when the feature becomes more important. Does that make sense? There are several, I think there's two main metrics for determining feature importance. I think they are outlined in this paper. I'm gonna look at this after this, and if it's not, I'll send out another resource. But these are the two main ways that feature importances are. There are two main ways that feature importances are determined, and just like looking at the effect of getting rid of the feature is one of them. All right. Next, I think, yeah, I talked about this earlier, but you can create custom ensemble models by using voting classifier, voting regressor, and it's actually intended to be used with conceptually different models. So for example, you know, so far we've learned KNN, we've talked about Bayes, we talked about decision trees, we've talked about logistic regression. So one thing you can do is actually take all of them and put them into a voting classifier, and then just take, like, you know, the average, or yeah, the average of the result. So within voting classifier, it says here that you can specify whether you want to use a majority class or soft vote. And majority class, you just, you know, majority vote. But soft votes, you actually take an average of probabilities. So most models actually will output like probability of being 1, probability of being 0, and then we'll just take an average of that, a weighted average of that. Also things that you can tune. So really quickly to think about how to, we don't have to answer this now, but common thing when in an interview you're asked what are the benefits of using a random forest, usually ties in with the bias variance trade-off, which we talked about earlier today and also a couple of weeks ago. How do random forests handle the bias variance trade-off? And then your answer should include basically something about the randomness in the ensemble method of a random forest. So basically in like selecting the random features at each split, or something about bagging as well will also contribute to this answer. But cool, after this is boosted algorithms, and like this first half took up all of the hours. So I will move boosted algorithms to Thursday. And then SVM I'll do during one of our study groups. But any questions to end off? All right, well, something I also want to check in on was that mini project that I sent out. What I'd like to see, I'll also put a message on Slack tomorrow, but I would like to see some of the results of the of some of the models that y'all have been running. Just like maybe what are some of the better models that you've tested, what are some good hyperparameters that you've tested for different models. Just to be interested to see. If you haven't been doing that, maybe discuss with your group members and talk about it. Questions about that?
Yeah, so now in the project itself, if we want to run this voting regressor itself, right, to find out. Now, what I did is, I'll be discussing with Henry and others, right? I selected few models, and then just I selected one of them, and I say, okay, this seems to be good, and right, that can be the final model for predicting.
Yeah.
Then in between, if I run this voting regressor and then decide, is it advisable?
Honestly, the voting, I sort of like to think of, you know, the voting classifier is an ensemble method, so you can sort of think of it as a model on its own. Sometimes the voting works better, sometimes it doesn't. Maybe you take like your like top 3 models and then put them into a voting your voting classifier and see how it works. But I don't think the order in which you're running things matters. Maybe like as we pick up the last few models of this mod, maybe you just like add them into your voting classifier and see how it performs as well. Maybe it changes, maybe it doesn't. But yeah, I think like the purpose of this mini assignment is really to, one, get used to running your scikit-learn models and like the scikit-learn syntax, but also just seeing how different models can yield different results. Hopefully that answered the question. Anything else? All right, well, I will post a message in Slack about that tomorrow. One last thing, which I'll also put in Slack tomorrow, is start taking a look at the Mod 3 project. I think it really benefited a lot of you the last time around to look at the project earlier on. So again, I suggest that for this project. With the tools that you have, we can already start working on the project. It's really just like a couple other models that we haven't talked about yet. So if you want to look at the project, do that. You do have a choice between 4 different data sets, and also you get to choose your own data set for this project. Only thing is, before you start working in your own data set, just send it to me and let me know what your data set is, and then I can just approve it and see if it makes sense for this project. I'll put that all in Slack as well.
Yeah, the expectations if we want to run a different data set.
Different data set. It has to be a classification problem. So you have to be predicting some sort of category. It has to be 0, 1. It also can be multi-class. Nothing wrong with that. So yeah, just any data set that has a column that you can classify whatever the data set is. And if it makes sense for that to be the column that you're predicting, should be fine. Good resource would be Kaggle for this. Cool. But nothing wrong with working on the pre-provided data sets. I also plan on like grouping you guys based on which data set you choose, so you can actually talk about it too. So yeah, just decide on your data set. I will put this in Slack tomorrow, so don't worry, and just let me know so you can start working on the project as soon as possible. This project is also definitely a solo project, so don't worry about having to work in pairs. All right, well, thank you for listening. If there are any other questions, do let me know on Slack. But if not right now, I will see you all at your one-on-ones or on Thursday. All right, have a good night, everybody.
Good night.